Hi, welcome to assignment 72, and these are differential applications. And in the last video, when we were talking about the change in the volume of the cube, we started to experience some of what does that mean. It looks like I've got 6 problems that I'd like to look at with you. And the first one is, what are we talking about? Estimate the change in the area of a circle as radius goes from 10 to 10.01. Okay. Estimate the change in the area of a circle as radius goes from 10 to 10.1. Okay, so now here's some important stuff to be thinking about. Estimate the change in area. Find dA. Okay, it's estimate. It's not the actual change. It's not delta A. It's our approximate change in A. And what do we have here? As radius goes from 10 to 10.1. So what that tells me is that dr is 0.1. The change in radius from here to here is that 0.1. And that is where we're building our tangent line. Okay, so I'm going to be using this for my radius. Radius equals 10, dr equals 0.1, and we want to know dA. Okay, so remember, pi r squared is our formula for area of a circle. And if I take the derivative with respect to r on both sides, I end up with dA dr equals 2 pi r. Remember, we bring down that 2, we leave the inside alone, but then we need to come back and take the derivative of the inside with respect to r. Oh, look, dr is just 1. So this is what we have now. Let's multiply both sides by dr. Tink. And so now I have dA is 2 pi r dr. Well, what was our radius? 10. 2 pi 10. What was our dr? 0.1. So 20 pi times 1/10 becomes 2 pi. And so dA is 2 pi. And if we had some units here, do we have some units? I don't know. Let's call them centimeters. So centimeters, centimeters. Change in area, this must be centimeters squared. And what is this saying? This 2 pi represents? Well, when I think about a circle whose radius is 10, and then I think about the circle whose radius is 10.1, this change in area can be approximated as 2 pi square centimeters. Okay? All right, what else do we need to do there? We estimated the change. Now I want percent error. Percent error. So what's this percent error? Well, the percent error is going to be dA over A. No, it isn't. That's the percent change in area. Percent change in area. Percent change in the estimate. I just don't like any of the English ways I have to describe this. So let's talk about this. This is your change in area as an estimate, as an approximation, and this is the actual area. And we want to know what amount of variation this is. What percent of the whole area is that? And so in the last problem, we said that dA was 2 pi. What's the actual area of the circle when r equals 10? So we have pi 10 squared. Well, that's 100 pi. That's the actual area, 100 pi, and our approximate change in area as radius went from 10 to 10.01 is 2 pi. So that's 1 over 50 centimeters. No, it isn't. Don't do it that way. Instead, you should say, aha, 2 divided by 100 is 0.02. And we know that as 2%. So dV is 2% of the actual volume. And depending on your needs, this may or may not be reasonable enough. Okay. All right. So then, let's take a look at. Was there something else I wanted to talk about? You know, I kind of want to go back to this thing that I learned in middle school called percent change. New minus old over old. And so for us, I could think about this new being that well, that's really tough love. You know, I'm looking at my notes here saying, well, so what we're doing here is comparing delta A. This is our way of saying what's the difference in the actual area and our estimate of the area. And not area, but the change in area. Actual change in area, estimate of change in area as a percent of the whole. Yeah, no, I'm sorry. You really don't have to worry about that. That's very old school. That's very, you're in honors AP Calc, and I'm not doing that to you in a pandemic. But I will say that dA over A, what percent is that amount of error in the actual area? Yeah, that one you need. Okay. The sides of a square increase from 3 to 3.01. Sides, this is open, yes, this is a new problem. Sides of a square go from, let's call that side x. X goes from 3 to 3.01. Okay, and so, you know, what do we want to do? A, estimate the change in area of the square as x goes from 3 to 3.01. So what I know there is I'm looking for estimate change in area when x equals 3, nearby convenient place, and dx equals, what's the difference between these 2 points? 0.01. Okay, so remember that dA dx equals, yeah, let's start fresh. A equals x squared. There's our area of the square formula. So then if I take the derivative with respect to x, I end up with this. If I multiply both sides by dx, I get dA, and I need to plug in an x value and a dx value, and I have those. My x is 3, my dx is 0.01. Right? So, and you need to be able to look at this and say, oh look, I'm starting at this very convenient nearby point, and I'm going a certain distance until I get to this point, and that change in x, well, that's my dx. So our answer here is going to be 2 times 3 times 0.01. So 6 times 0.01 is 0.06. Okay, and we could certainly look at what's the actual change in area. You know, we could say, hey, what's A of 3.01? And my calculator says 3.01 squared equals 9.0601, as opposed to A of 3, which is 9. And so what am I looking at as the difference? I'm looking at 0.0601. This is the actual change in area. This is my delta A. This is my estimate, my dA, my estimate in change in area. Look, tens, hundreds, thousands, 10,000s. They're within 1/10,000th of each other, so I feel pretty comfortable with that. Now, what about, what about, don't lose all that information, what about this dA over A thing, right? This approximate change in area, how big a deal is it? You know, when I compare it to the actual area, well, that's going to be 0.06 over, what was the area when x equals 3? 9. So what are we going to have there? 0.06 divided by 9, and I end up with 0.00666, etc. So, you know, it's and these are percents. This is now a percent, right? Because I'm doing what I had versus what there was, and so I'm looking at 0.667%. That's what this is with respect to that. It's less than 1% of the total area, I guess is the way I want to describe it to you. You know, if my total area is all 9, this 0.06, this approximate change in area, really only represents a little more than 0.5% of the whole area. Okay? And then the problem takes an interesting turn. We've been doing those things, but now check this out. If we want the change in area to be within, does it say 1%? It does, 1% of the actual area. What error is okay in measuring the sides of the square? Okay, so error in measuring the sides, error in side, variation in side length. So that's my dx, and I don't know what it is. Do we want to say, and is this the same problem where we're talking about, no, we actually don't need to worry about it. Okay, I was looking to see if I needed to know side length, and I don't need to know side length here. I'm looking for dx, and the change in area, dA, must be within 1%, 0.01, of times the actual area, A. So, where are we going with this, Kukla? Well, yeah, so here we are. A equals x squared. dA dx equals 2x. Multiply both sides by dx. dA equals 2x dx. Yeah? But we don't know this. And we do know that the error in area must be within 1% of the actual area. So I'm going to replace dA with 0.01a, 2x dx. And I imagine you're saying to yourself, okay, how does that help? Well, remember, area is x squared. So I'm going to now say 0.01 times x squared equals 2x dx. Now, what were we trying to find? We were trying to find what amount of error, what amount of variation, what amount of change in x can we tolerate if we want area to, the change in area to be within 1% of the actual area. Yeah? And so now I'm going to say, great, well, let's just divide by 2x. And so what happens here? This cancels that. 0.01 divided by 2 is 0.005x equals dx. Now, this is actually really easy and really important. The error in measuring the side length can be within 0.5% of the actual side length. So, error within 0.5% of the actual side length. Okay? Now, I need to text Dodie something before I go on. So please read this again. think about this again. What were we given? What were we looking for? Did he really say that dA was equal to 0.01a? And where did he go from there? Okay, review your notes for a moment. I'll be right with you. Okay, I'm back. Thanks for waiting. Yeah, so notice I didn't need to know what the area was. I didn't need to know what the side length was. I just built everything based on these relationships. So I'd like to do a couple more like that, all right? And of course, we could then, do that. No, I think that's plenty. Let's not do any more. Sorry. Very eager. Down, boy. Okay, if the radius of a sphere goes from 3 to 3.1, find the percent change in V. And a percent change in V with respect to original volume. And what is this trying to tell me? These words are trying to tell me we want to know dV over V. Okay, so let's see what we've got. My sphere, radius, change in volume. The radius, we should find the change in volume. Yeah, so we're looking for dV, and we know radius is changing. What can we say about dr? Radius changed from 3 to 3.1, so dr must be 0.1, and we're going with that starting convenient radius of 3. Okay, I just need to find dV now, so let's see about that. V equals 4/3 pi r cubed. Yes, you do need to know the formula for the volume of a cube, and if you don't, you should put it on that page of notes that I've been nagging about all year, where you write down formulas you've forgotten. So then dV dr is going to be 4 pi r squared, right? I bring down the 3, those cancel, 4 pi, I subtract 1, r squared. Multiply both sides by dr, and so we get that dV is 4 pi r squared dr. We know that r is 3, we know that dr is 0.1, so we're going to have 4 pi 3 squared times 0.1. And that's going to be 9 times 4, 36 pi times 0.1 is 3.6 pi. So 3.6 pi is our dV. But remember, this is asking us to find that what percent of the whole original volume is the change in volume. Well, the change in volume is 3.6 pi. And what would the actual volume be at 3? 4/3 pi and 3 squared cubed. Sorry, 27 divided by 3 is 9. 9 times 4, 36 pi. And I get 36 pi. Well, dink, and what can you say here? Gosh, if this were over here, it would be 36 over 36, but because I've moved over 1, there we go, 0.1. And so I think that's 0.1. So the error in volume is approximately, because it's an estimate, approximately 0.1 or 10% of the actual volume. And that seems pretty big to me. I mean, I don't know if it is or not, but I imagine if I had, some sort of Pokeball machine, and I needed to make sure that my Pokespheres fit in the machine, or gosh, what happens if the radius on the Pokeball machine slips from 3 to 3.1? What's that going to be? Whoa, it's an extra 10% of volume. Yikes. So that's what I can do with that. Okay, now how about number 4? Volume of a cube when the sides change from, what are we changing from? We're changing from 6 to 6.01. Volume of the cube. How about the change? Ooh, that's it. Estimate the change in the volume of the cube when the sides go from 6 to 6.01. And, you know, of course, you could do 6.01 minus v of 6, and you could get the actual change. You know, that's our delta v. But we want to estimate the change, and so we're looking for dv. Okay, so why don't you find dv? Hey, welcome back. So we're looking for dv, and we know since v equals side length cubed, volume of a cube formula, that dv ds is going to be 3s squared. And if I multiply both sides by ds, I can see that dv, the estimated change in volume, is going to be 3 times, what's our side length? 6 squared times, what's our ds? We're going from 6 to 6.01, so ds must be 0.01. 36 times 3, 108 times 0.01, and so we get 1.08. I feel like we just did this problem. So there we go. That's the first part. Now, we've got that change in volume. This is our dv. That's great. You might also be asked about dv over v. You know, what part of the entire volume is that error or change in volume? So we've got 1.08, and we had a side length of 3, wasn't it? Oh, maybe that's why this seems familiar, because blind Kukla was looking in the wrong place. No, 6 to 6.01. So our v of 6 is 6 to the third, or 216. So that turns out to be 0.005. Or, how do I understand it? The estimated change in volume, dv, is 0.5% of the actual volume. How did I know that? I moved the decimal point over 2, right? Because if you had 0.02, you'd say, oh, that's 2%. Well, I moved my decimal point over 2 and got 0.5%. So within 0.5% of the actual volume. Okay, next. Same problem, right? We're still talking about this cube whose sides go from 6 to 6.01. And now they say, find the error in volume when the side length is within 1% of its actual value. Yeah, the cool thing is we know what all of those words mean, and yet so many people look at this and say, I don't know what the hell I'm supposed to do there. So let's name some things calculously. Within 1% of its actual value. What? What is this referring to? Side length is within 1% of its actual value. And it's not the side length. It's actually, it's a little sort of hidden parenthetical. It's the error or change in side length is within 1% of its actual value. And I think, change in or error in side length, I'd love it if that textbook, when it came out in its new edition, put a clarification there, because right now, how am I supposed to know that? So, the error in side length, ds, must be is within 1% of times the actual value. The actual value of what? The actual value of the side length. So this is my helping equation. Now, about that error in volume you were asking about. So we're looking for dV. We've been given some information about ds, and we've been told that this object is a cube. So let's think about that. We know that v equals x to the third. X, or am I using s? I'm using s, sorry, s. So then dv ds is going to be 3s squared times ds. Now for us, we know that, I multiply both sides with ds, there we go. We know that dv equals 3s squared times ds. For us, we've been told that ds is 0.01s, so 3s squared times 0.01s. Now look what happens. S squared times s, 0.01 times 3, so I'm going to have 0.03 s to the third is dv. Now, what's s to the third? Yeah, it's volume, isn't it? 0.03 v is dv. And what does this tell me? This tells me that the error in volume, the change in volume, the approximate estimated change in volume is 3% of the actual volume. And are you really ready? 3%. This change in volume is 3% of the actual volume. We've been looking at it, and now they connect. Yeah, it's really powerful. You may want to watch this again. Okay, so that was the error in side length is 0.01. Let's go back and do the same problem, but let's say this time that we want to find the error in side length, or the change in side length, if volume must be within 1% of its actual value. Now, be careful here, because again, it's not the volume. It's actually the change in volume that they're talking about here. The change in volume must be within 1% of its actual value. The change in volume must be within 1% of the actual volume. Great, we've got that. We want the error in side length. They want to know, what can we say about ds? Okay, well, let's talk about this cube. V equals s to the third. Let's say that dv ds equals 3s squared. Let's multiply both sides by ds. And now we've got change in volume. Fabulous, which I can put that in for. 0.01v equals 3s squared ds. And what are we looking for? We want to know the error in side length. I mean, naming these things calculously can really, really help. Think intentionally about taking these English words and how do I describe that calculously? The error in side length, the variation change in side length, that's my ds. The change in volume must be within 1% of its actual value. Change in volume is 1% of the actual volume. So we're almost done. Let's take a look here and say, v, I know that v is s to the third. And then I come back and I divide by this 3s squared here. And look, these cancel two of those, and I have 0.01. Yeah, I'm going to screw up that decimal. So let's take out the calculator. 0.01 divided by 3, and we've got 0.00333 s equals ds. Now, how am I supposed to understand that? Well, I can understand that two different ways. The first way is that the error in side length is 0.333% of the actual side length. Ooh. But wait, there's more. What if we divide both sides by s? And then we get 0.00333 and so on equals ds over s. See it there? The percent. What percent is that change in side length? Okay, well, have a wonderful day, everyone. There's all kinds of chimes for you right now. Bye. Okay, somehow I thought it would be smart to make another video while you were moving. And so your timing is excellent. How can I help you? Did that not work? Yes, but I actually may be able to, look it up on my computer. So let me try finding what that password will be. Oh, look, here's Synergy now. And it seems to have a bunch of digits, but let's say that Chrome must know my password, or it wouldn't be offering to autofill it. And but of course, this is the computer that goes very slow. So I've got passwords. I'm looking for Synergy. Does that come up? Yes, it does. And I'd like to see that password, please. Know that password. Okay. And it seems to, oh my goodness. Steve 3, capital S, Steve 3. And then there seem to be 3 exclamation points. Yeah, does that work? Perfectly. That's amazing. You are godlike in many, many ways. No, thank you so much, Rusty. Take care. See you in a bit. Rusty's bringing me a laptop. Well, so the cool thing about these laptops is that if you don't log in to SourceUp at a site,
it isn't attached to the VPN. But if you do it,
so if you go to school, got it, the online information is now doing that. To try and figure out how to drive up there. Looking a little 20-something.
how's the little jean situation there?
It's I myself feel like the tight jean is even in the early 80s when people were, that's uncomfortable. That's like, why would I need to shave my legs? I'm just gonna wear the tight jeans.
Mm-hmm.
But I will say that it's really hard for me because the old you of last year still so beautiful. But it's finally free, and that's what I do. And
they're a size 8.
And they're a size 8, damn.
She said, I think those might be too loose on you. Try size 8.
Wow. I wish I could say things like that to you. Oh, it's still recording. Oh, it's still recording.